Hi everyone, I'm Hendrik Bayer, and this talk is about some work I've done with Michael Kaisers on a search algorithm called Opponent Pruning Paranoid Search. This work is primarily applicable to deterministic, perfect information multiplayer games, that is, games with more than 2 players. In the following, I'm going to quickly outline the state-of-the-art Minimax-based search algorithms for these games, as they form the baselines for our later experiments. The classic multiplayer approach named max-n search is based on the idea that every player at every internal node of the search tree maximizes their own individual utility when it is their turn. So when you look at the leaves of this toy tree, you'll see that every leaf node is labeled with a vector of utility values for the 3 players. And every player chooses a move that maximizes their own utility when it is their turn. Now, max-n is very intuitive and converges to an equilibrium in the limit, but it has 2 major weaknesses. First, deep pruning, like in 2-player alpha-beta search, is not possible, leading to pretty shallow trees. And second, max-n can be too optimistic, because it assumes that no opponents ever form coalitions against the root player. Paranoid search now takes the opposite approach, of assuming that all opponent players always form a coalition against the root player. This effectively turns any multiplayer game into a 2-player game between the root player and the coalition, which makes deep alpha-beta style pruning possible. As you can see in this toy tree, the vectors are gone because only the utility values for the root player matter here, which are maximized by the root player and minimized by her 2 opponents. Paranoid tends to outperform max-n in practice due to the deeper searches enabled by alpha-beta style pruning. However, it suffers from being overly pessimistic, especially with deeper searches and with higher numbers of opponents. In many games, it's ultimately not possible to win if all opponents form a coalition against you. 2 improved algorithms based on paranoid search are best reply search BRS and the current state-of-the-art BRS+. These algorithms still assume that all opponents are playing against the root player. However, they restrict the move choices of this coalition. In BRS+, only the opponent with the strongest move against the root player can choose this move freely, while all other opponents have to choose the move ranked first by a move ordering heuristic, and so have their branching factor reduced to 1. In this toy tree here, the highest ranked move at every node is marked in bold, and you can see that between any 2 nodes of the root player, at most 1 opponent is allowed to choose a different move. This restricted move choice of opponents allows for even deeper search and more long-term planning than in vanilla paranoid search, and it also weakens some of the pessimism of the paranoid assumption. All opponents are still playing against the root player, but their moves and therefore their strength as a coalition are somewhat limited. Now, BRS Plus is currently the state-of-the-art Minimax-based search algorithm for fully observable deterministic multiplayer games. The new algorithm we're now proposing, Opponent Pruning Paranoid Search, or OPPS, is a direct generalization of it, as I'm going to explain on the next slides. BRS Plus essentially divides the opponents of the root player into 2 groups. One group of only 1 opponent, who is allowed to freely choose a move, always the 1 opponent that can hurt the root player the most. And another group with all other opponents, who have to play their highest ranked move. OPPS generalizes this by introducing 3 parameters. N1 is the number of opponents in the first group with the wider move choice, which is always 1 in BRS+, but is the first freely tunable parameter of OPPS. L1 is the corresponding upper limit to the branching factor of this group, which is infinite in BRS+, but gives us the second parameter of OPPS. And L2 is the upper limit to the branching factor for all other opponents, which is always 1 in BRS+, but represents the third parameter of OPPS. L2 is always smaller than or equal to L1. So just to clarify, both L1 and L2 here are limits on the number of top-ranked moves as ordered by the static move ordering. For example, L1 equals 8 would mean that the first group of opponents can choose from the 8 highest ranked moves. As you can see here, the existing BRS Plus is simply a special case of OPPS with fixed parameters 1, infinity, and 1. By varying these three parameters, however, OPPS can more smoothly adapt both its degree of tree pruning as well as its degree of paranoia or flexibility of the opponent coalition to whatever works best in the domain at hand. Now, depending on its parameter settings, the tree searched by OPPS can be either larger or smaller than the tree BRS Plus would search. This is illustrated on this slide and the next one with the trees searched by two different OPPS parameter settings. In this toy tree, we can see that while the BRS Plus tree we've seen before had 10 leaf nodes in total, the tree of OPPS with parameters 1, infinity, 2 has more leaves, 16. But the tree of OPPS with parameters 0, x, and 2, where the value of x doesn't actually matter, has only 8 leaves. And these small differences in tree size grow exponentially with tree depth and really influence playing strength, as I'm going to show on the next slides. So let's get to our experimental results with OPPS playing against the baseline algorithms and some further analysis of what these three parameters really mean for search tree growth. The test domain for all experiments reported in the paper is Chinese checkers because it's a relatively well-known multiplayer board game which allows to scale the number of players from 2 up to 6. However, I'm hoping to soon have results ready for a number of other multiplayer games as well. All data points are based on at least 1000 games, and all experiments used a fixed search time per move. The algorithms were therefore implemented with iterative deepening. Our experiments are divided into 3 sets. In the first set, OPPS was compared to its special case, the current state-of-the-art multiplayer search technique BRS Plus. We used time controls of 50, 250, 1000, and 5000 milliseconds per move in Chinese checkers with 3, 4, and 6 players. The parameters of OPPS were tuned for each playing condition separately. As we can see in this chart, OPPS is significantly stronger than BRS Plus in all game variants and time controls, with the exception of the 3-player game at 250 milliseconds, where the difference did not quite reach significance. We can make 2 more interesting observations here. First, OPPS is able to scale better than BRS Plus with the number of opponents. The average performance over all time controls increases from 3 to 4 to 6 players, as you can see at the bottom. This is very promising for future work on domains with even higher numbers of agents. Second, the performance of OPPS can vary quite a bit with the time controls, something we discuss in more detail in our paper. Now, the baseline we just used, BRS Plus, has been shown to be a significant improvement over MaxN and Paranoid in the literature in a variety of games. However, we wanted to make sure that our tuning of OPPS against BRS Plus had not led to overfitting, and that OPPS was indeed still outperforming the older techniques MaxN and Paranoid as well. In our second set of experiments, we tested this at 250 milliseconds per move, with the same parameter settings that were found to be optimal against BRS Plus before, without retuning anything. And we indeed found that OPPS is much stronger than both MaxN and Paranoid in all variants of the game. The third and last set of experiments finally looked at how fast search trees grow with search depth. We used 4-player Chinese checkers here, and we compared MaxN, Paranoid, BRS Plus, and 2 other variants of OPPS, namely OPPS 151 and OPPS 1 Infinity 2. The resulting average search tree sizes for different search depths are plotted in this figure. It shows how much smaller search trees for the same depth can get when moving from max n to paranoid, and then again when moving from paranoid to BRS+. And the additional plots for OPPS 151 and OPPS 1∞2 show how the parameters of OPPS allow it to fine-tune the tree sizes to what works best in the domain at hand, being able to do more or less pruning than BRS+. And this brings me to the last part of my talk on possible next steps. We see several interesting directions for future research on multiplayer games. Let me just briefly mention two here. First, the design of OPPS could be generalized further to make it even more flexible and adaptable. Instead of using only two groups of opponents with a fixed size and a fixed branching factor limit each, we can easily imagine a generalization to more groups, maybe even in an algorithm that makes the choice of branching factor in every node of the tree dynamically based on features of both the game state as well as the current state of the search. This idea could also be generalized to games, for example, featuring indeterminism, simultaneous moves, or imperfect information. We see OPPS only as a first step here. And second, the idea of abstracting away some of your opponents, or some of their move choices, in order to be able to focus more on your own planning, is also promising to explore more deeply in the context of the Monte Carlo tree search framework instead of the Minimax framework. In MCTS, for example, alpha-beta style pruning is not possible, and the paranoid assumption has not been shown to work yet. But abstraction and pruning or unpruning of moves have been studied in some depth. We now actually already have a paper out on this translation to MCTS called Guiding Multiplayer MCTS by Focusing on Yourself, and published at this year's conference on games, so please do check that out as well. And that's the end of my talk. Thank you very much for watching, and goodbye.